Question 5.2. We have a system, and the system is an ideal low-pass filter. So we have a system this is an LTI system. Well, it takes input, say, x of t, and gives the output y of t. Alright, so this is an ideal low-pass filter with cutoff frequency 4 radians per second. We are looking for output in frequency domain. This is output in frequency domain, and also we're looking for output in time domain. So what we have the input in frequency domain, and so if you look at the expression for this input at frequency domain, you see that if I want to plot that, it looks like this. Say this is omega and this is x of omega. If you look at the expression, you see for values for the frequencies higher than 5 radian per second, the value of the x of omega is 0. Okay, this is 5 radian per second, and also for values below minus 5 radian per second. And for the values for the frequencies between minus 5 to 5 radian per second, it has some values different from 0, which we don't care about the value at the moment, but we can plot that here. So that means I can, instead of this expression, I can write it using a rectangular function. All right, because you see this looks like a rectangular function. Instead of this expression, we always can use a rectangular function, and that would be like I can write this like x of omega equals e to the power of minus j times 3 times omega times a rectangular function. And the rectangular function is going to be 1 when the frequency is in this range, because this value times 1 remains this value. And it's going to be 0 for the frequencies out of this range. And when it is 0, 0 times e to the power of minus j times 3 times omega is 0. Okay, that's exactly what we want. So what should be the rectangular function like? Well, if you look at here, we say the rectangular function should be 1 in this range, and that means the rectangular function should be omega over 2 times this frequency, cutoff frequency, which is 10. So let me write it here, omega over 10. So that's another expression for this, for the input signal in frequency domain. Okay, so we have x of omega, which equals we don't need to write it here. Okay, we have x of omega, and we know that this is the Fourier transform of small x of t, or the input signal. Okay, we're looking for this y of omega, the output in frequency domain and output in time domain, both. But this is not enough to find the y of omega. We should look at the system, we should look at the question to see what kind of information we can get. Well, as we said, the system is an ideal low-pass filter with cutoff frequency omega c. Let me plot that frequency response of this system. Well, the system is an ideal filter, and that means the frequency response of the system is 0 for frequencies higher than 4 radian per second or smaller than minus 4 radian per second, and is 1 for frequencies between minus 4 to 4 radian per second. Okay, so let me write it here. Okay, so we saw that we can write h of omega equal, actually we can express that using a rectangular function. It equals a rectangular function with omega over 2 times frequency, cutoff frequency, or 8. All right, so we have a system, and the frequency response of this system is a rectangular function, omega over rectangular function with omega over 8. Now, can we find the output in frequency domain or not? Well, we know that the output in frequency domain equals the frequency response times the input in frequency domain. Well, we have these two guys here, so we can simply calculate the y of omega, the output in frequency domain. So y of omega is h of omega, which is a rectangular function, omega over 8, times x of omega. X of omega is e to the power of minus j times 3 times omega times rectangular function omega over 10. So let me write it in this way. Omega over 10 times e to the power of minus j 3 times omega. So this is the y of omega. Well, can I further simplify this? We have to rectangular function. We first want to see whether can we find this multiplication or not. So let me just plot it here. That would help to better understand this multiplication. So let me plot the first one. This is the first one. Or let me use a okay, this is rectangular of omega over 4, and this is omega over 5. Sorry, omega over 10. If I multiply these two rectangular functions, rectangular signals, you see that for values like when either of this or this is 0, then the multiplication is 0, and that means for all values here and here the multiplication is 0. But for the values that both are 1, both signals are 1, the multiplication of the signals are also 1. So the answer is this yellow one, okay, which is actually rectangular of, if you check, it is rectangular of omega over 8. So I can then write this y of omega equals rectangular function omega over 8 times e to the power of minus j 3 times omega. So we got y of omega, and now we want to find y of t, the frequency response in, the output in time domain. And that's, if you want that, we need to just take the inverse Fourier of y of omega. So y of t is inverse Fourier of y of omega, and that's from chapter 3. Now let me write it here. And from chapter, from chapter 3, let me make some stuff, some space here, and we know that the inverse Fourier transform of a rectangular function. omega over 8 is a sinc function, sinc of 4 times t over pi, and this is 4 over pi. Okay, that's we can simply calculate it from what we learned from chapter 3. And if I multiply this one to e to the power of, say, minus j delta t omega, that equals a time shift here. So let me write it in this way. The inverse Fourier transform of a rectangular function omega over 8 times e to the power of minus j delta t omega. This equals 4 over pi times sinc of, not sine of, sinc of 4 times t minus delta t over pi. Okay, and here the delta t for this case is 3. So delta t is 3. So I can write this and say y of t, which is the Fourier transform, the inverse Fourier transform of a rectangular function, omega over 8 times e to the power of minus j times 3 times omega, equals 4 over pi sinc of a sinc function is this parameter 4 times t minus 3 over pi. So this is the y of t, or the output in time domain, and that's the end of this question.